So our next speaker is Dr. Matteo Menolotto. Dr. Matteo Menolotto is a researcher at Tyndall National Institute working on wearable technology and developing human-robot interface technology to foster the new frontier of collaborative robotics. In his talk, he will guide you through the open questions and latest research trends in the so-called smart manufacturing field, with particular focus on the technology that is enabling the safe interaction between robots and human operators. He will talk about how the robotic revolution is rapidly accelerating, with thousands of robots already having been deployed in many industrial sectors worldwide. He will discuss whether this will be just a huge opportunity for large companies and if job places are at stake. Matteo?
Yeah, thank you very much, and good evening, everyone. And I'm Matteo. I'm a postdoctoral researcher at Tyndall National Institute, as you have heard. And in the next 12 minutes or so, I'm going to give you a general overview, let's say, on the research activity I carry on in the field of human-robot interaction technology, and more broadly on the so-called smart manufacturing revolution, which is rapidly changing the paradigm of how we produce goods and services. Hopefully, along the way, we will also try to clarify some doubts and maybe debunk some myths and misconceptions. So to help me in this journey, I will use the aid of some nice slides. So there you go. So, okay, just a little bit of about me, let's say. So I was born in Venice, and I did my bachelor and master degree in Italy in electronic and biomedical engineering. Then I moved to Glasgow for my PhD in biomedical engineering as well. And finally relocated in Cork in 2019, like Melusine, a few months before the whole nice COVID thing. And here I started to work as a postdoctoral researcher on smart manufacturing and collaborative robotics. So yeah, I moved a lot, and but here we are. So let's begin with the main question: what is smart manufacturing? You might also have heard the terms smart industry or Industry 4.0, even though I'm not a big fan of this last term. But these terms, they all refer to the integration of digital technologies to the manufacturing process. So in particular, the introduction of automation, sensors, and real-time data processing. And I think it's important to highlight that despite the technological advancement is generally quite fast, this process has not started in a specific time. In fact, the industrial world is constantly and slowly incorporating any mature technology that is being developed so far, which is why actually I don't like to match the term Industry 4.0. It's catchy, and it definitely conveys very effectively the meaning of technology that goes a step forward. But it's important to say that this advancement is not a linear process. It's rather the result of many different lines of research that some of them succeed, some of them just drop. Similarly to the human evolution, we all have seen this famous image in many versions where there is like a monkey that slowly starts to walk and at the end becomes a human. But in reality, what anthropologists are discovering, and actually they know that since a while now, is that this vision is a very rough simplification and ultimately wrong. The evolution is more like a tree with many branches that coexist at the same time. Some of them fall down, others go on. And technology is very much similar to evolution, I would say. So after this little philosophical tangent, let's go back to the topic. The real game changer, I would say, in this revolution are data. we can now easily measure a lot of physical phenomena, and these, with those data, we can build models that we can use to predict a specific behavior or to control a specific effect according to our goals. Let's make a few examples. So if you want to keep the room temperature at a specific value, let's say in the summertime, maybe not here in Ireland, but let's say in our classic summertime, we can use the temperature we can measure the temperature with a thermometer, and we can easily implement a system that when the temperature goes, let's say, above a certain value, switch on the fan. So now this is a very simple system where the information about the temperature is used almost directly to modify or to control the parameter that the sensor is measuring. Another example could be measuring the posture of someone lifting a box, for instance. Now, there are two ways to lift a box. I don't know if you know that, but I can answer this question. So there is a wrong way and a right way. And or better, to explain better, there is a specific body configuration that minimizes the stress to the skeletal muscle system while lifting. So now we can place, for instance, an inertial sensor on a vest, and inertial sensors can detect the direction of the gravity force. So they are usually used to track the orientation of an object in the 3D space. And now we can actually build this vest and make the worker to wear this vest. And there are models already that tells us that if your back tilt over a certain angle, your risk to have injuries increases. So we can measure how vertical the back is during the task, and we can, for instance, launch a warning to the worker if his or her position can cause some harm, preventing him or her from having injuries or muscular pain. And that's it. So why this last example? Well, this last example actually finally allow us to jump into the field I'm working on at the moment. In particular, my group is very active in the development of wearable technology, which are devices that, as the word says, can be worn or that can be, in general, portable and able to measure some parameters out of the persons, like pretty much like Melusine said about the contact lens for cow. The classic example you can think of is the smartwatch, for instance, where there are smartwatches that can measure how many steps are you taking, or now also the heart rate and other parameters. Now, the one you see in this slide is the Tyndall Smart Glove, which is a project actually I joined and I'm currently working on. And it is used to track the orientation of the hand in the space via the same inertial sensors that we were talking about before. And I also put a picture of one of our lab that we use to develop this technology. There's quite a lot of things going on in that lab, as you can see, but I wanted to highlight especially the camera, the little cameras there. And that is actually a very accurate motion capture system that we use to evaluate how accurate is our technology. So as you can see, the glove could be used for virtual reality applications, given we can recreate a virtual avatar, for instance, of our hand with the orientation of each part, palm and fingers included, and we can track it in real time. The idea here, though, is to use the glove also as a human-robot interface for teleoperation application. So for control remotely a robotic arm, for instance, or a gripper, or a robotic system in general for collaborative robotics applications. Now, collaborative robotics is a very fascinating field that has been enabled by the use of this technology. In a collaborative robotic scenario, operator and worker works together. operator and robot works together, sharing the same working space. Now, this, of course, raises a hell of an issue in terms of safety, primarily, which is being addressed by implementing different strategies, the majority of which adopt sensors, once again, to detect the position, for instance, the position of the worker and the position of the robot in real time in order to avoid collisions, just to name one. But there are also other, actually a lot of research topics that are trying to tackle this problem from different angles, are aiming in making robots, for instance, intrinsically safe. And we will see later, actually, what I mean with intrinsically. Why collaborative robotics is so attractive? Well, it's not just for its technological flavor. It's mostly because of its flexibility. So the capability of readapt to different tasks, being easily reprogrammable and relocated in any part of the industrial compound where it's mostly needed, without impacting on the existing infrastructure. And as you can imagine, this means that automation becomes much more accessible and affordable to also medium and small scale industries as well, which can therefore they can get all the benefits of automation, expanding their production and their employability as well. Still, one of the great challenge to fully enable this scenario is safety, which should be implemented at different levels, let's say. So if not, actually, even in the design process itself. So in that sense, I said intrinsic. And here is an example. So to explain what I mean with intrinsic, I brought this specific example, which is the so-called soft robotics. So it's a kind of robotic that is inspired by nature. And basically, they are trying to create a naturally compliant robot, which do not just make the whole human-robot interaction much easier, much safer, but also solve a lot of other open problems in robotics, especially object manipulation and navigation. Here you